Hi, Derek and everyone. Thank you a lot for your question, Derek. It's really a good question because it indicates that you have been thinking a lot about the Ohm's law, also about like non-ohmic material. So let's see the question. How does the change in resistance in non-ohmic materials affect its voltage? And then you also have some idea that increase in current increases the temperature of the object, causing more atoms, vibrations, and increased resistance. But how does it affect voltage? Okay, so I could say like these quantities, voltage, resistance, and also current, like the intensity of the flow of electrons um, in the wire, in the materials, are three quantities that strongly related to each other that have been studied by Ohms, and then he figured out this relationship, right? But the key things here is that based on your question like this, you say how does the change in resistance affect the voltage? It implies to me that you think that the resistance will affect the voltage. So it seems like in your opinion, from your understanding, I would understand like resistance is like the cause and then voltage is the result, the consequence. Then you also think that you see that increase in current increase the temperature of the object. So again here I would assume that from this statement the current should be like the cause and then the temperature is the result, and then this result again causing some atoms vibration and increase the resistance. So seems like the resistance is the final result, right? You have a series of relationship, like the current will affect the temperature, and then the temperature will affect the resistance, and then from this resistance here, right, it will affect the voltage. That's why you ask like, how does it affect the voltage? So I would say like, this is a very common misconception, okay, that not only you but I also like have found myself in the past not very clear about this relationship, and maybe other students and many other people also have this misconception for a while. So let's clarify this one, okay? This is a misconception because what? Because this is not the relationship between them, okay? So what is actually the relationship between these one? First, let's just have the statement of the Ohm's law again. So what does he say? So basically that what did he do, or like what do we really do in the lab, in the experiment? So actually you will start with some wire first, right? You should have some copper wire or some wire or some materials of different resistance. So resistance is a property, it's a property that depends on the material. So this is a materials property. So just like you are you and I am me. So each of us have our own personality. So it's just the same for like material have its own resistance. It also depends on the material structure, the atomic structure, if we really want to look deep into it. And later we will look deep into to explain about how the resistance different varies between different kinds of materials, okay? I will save it for later. But here I just want to emphasize that resistance is a materials property. So it just exists there from the very beginning, okay? Next, for the voltage. What is the voltage? So actually when we have like a battery, with a positive and a negative terminal, and then we apply it at the two ends of a device, then we say that we have put a voltage. It means a different potential. Let's say this is like the point A, and then this is the point B. Then between A and B there's a difference in voltage. in a electric potential VA greater than VB, then we said okay, there will be a voltage across this device, right? And here this should be like a resistor with a resistance R itself. Then we can see that okay, this is the change. The voltage here should be the difference in the potential energy between A and B, and it will be like the higher one minus the less one. So usually we have the voltage resistance like this without the delta, right? But basically it means that this is the difference in potential, electric potential, okay? Okay, so this is a voltage across, and so what does it depend on? So actually voltage depends on the battery, right? It depends on the battery, and sometimes if you have like depends on how you wire the stuff together. If you have two resistors parallel to each other, or if you have like this resistor like in series with each other, so then we can see that not only like the voltage applied here depends on the battery itself here, you know, but also like we can see that the voltage across each resistor here will change depends on how we wire the system. So does it answer your question now? It is not the materials or the resistance affect the voltage, okay? But it's the battery itself, or like the way you wire everything in your system, okay? So what does it really mean here? I think that what you try to understand is just the relationship between all these. So by Ohm's law, it actually means that the current, okay, the intensity of how many electrons flow through a cross section of the wire per unit of time, how many of them the currents flow, right? It depends how it depends on the voltage. So we can see this is a positive correlations, right? When you got V increasing, you also have like I increasing usually. And also for the R, you also have like if R increasing, then this is a inversely proportional relationship. So if this one like increasing, this one like decreasing. So if the materials follows the Ohm's law or obeys the Ohm law, then this is how we have it. This is how the trend line, the relationship of the I and the V is expressed. And this is just another reminder. I will say that whenever you see some materials, if they got something like V and I here, I don't think that is a very accurate expression way to try, you know, because this one basically just show us the correlations, but not the nature of the electrical concepts here. Why? Because here you see this is the independent x, so then this one should be like something that exists before, you know, that it should be something like the cause, you know, if this is a causality relationship. So then the dependent variable should be like the consequence, the effect after something changed on the x. So that's why the proper way to express the Ohm's law should be V is in the horizontal, okay, axis, and then I, the current, should be in the vertical axis because this is the independent variable and this one is the dependent variable. Okay, so basically with this one, you should have this is a linear relationship if you got the R does not change, if it's a constant over time. So then we can see if this one going up like this, okay, and if this is the I, if this is like the X, then we can see that the slope here will equals to I over V. So actually the slope here equals to what? So just based on the Ohm's law, we can see that it equals to 1 over R. You see the slope in this graph IV is actually 1 over R. And when you got the resistance doesn't change, then by the Ohm's law, This is a linear one. Sounds good? So that's the first thing. And what I want to highlight is that maybe you can see some figure like this is very helpful. It's very helpful. I like those. That it means, okay, this is stop resistant. I don't want more electron flow through. Okay, so this is resistant. But like for this one, it's really funny, right? Like we got a resistance measure in ohms here. That's why we got this one wearing a hat like with ohms. And then you got the amperes, like this is the current measured in amperes trying to get through. And then voltage is like the electromotive force trying to push the current through. This is pretty good to express it. But because we kind of used to like with this kind of expression, V equals I times R. So sometimes we forget that this one is actually the dependent variable. It should be expressed this way, okay? Physically meaning it should be like this. This is just like a math form for convenient in calculation, okay? This is the proper expressions of the Ohm's law in a physics sense, okay? And actually here you know that nothing changed with the shape of the Y, right? It's just that it tries to illustrate that this one is not easy to get through. That's the point. So I could want to highlight that. Remember that those is easy to understand, just to have like a funny sense, but to think about it really accurately, physically, remember this, okay? And remember this, okay? So that's it for the ohmic conductor first. And then in the next video, I will explain more about what could happen for these kinds of craft when it's like non-ohmic material. Sounds good? Okay, see you soon. Thank you.